Hello, this is our last section. We will talk about numerical methods for solving differential equations with MATLAB. Last semester I did not cover this section, we didn't have time. But now I want to just show you a couple things that I think you will be needed. It will be, good for you. To be able to solve a very basic differential equation, ordinary differential equation like that, in MATLAB, it's so easy. What you need to do is you need to define your right hand side function, cosine t. So this f is the cosine t, and t is the time span that you want to solve this differential equation, and s0 is the initial value you need to give. So for example, for this one, cosine t is our f, t is 0 to pi. You can see that 0 to pi here, and also s0 is just an initial condition. It's given as 0. So if you do that, you can easily find the solution. This is the right hand side solution with the at comment we defined. We said that it will depend on t and s, cosine t, and here our f is in there, and our t is from 0 to pi, and initial value is 0. And now t is the time, s is the solution of your differential equation, s, and you can just plot this solution as you can see here. So this is the numerical solution. Of course, you cannot find the solution with a function, and here this is the error. I just added for you s of t and sine of t, because this differential equation has a solution sine of t. It is easy, and that's why from numeric to real solution you can see that this is 10 to the minus 7, and the result is not bad. And similarly for this one again, for f we are defining the right hand side minus s of t with t and s, and from 0 to 1, and this is the solution, this has the solution exponential, and the same way we are plotting our solution. It is exponential e to the minus t, and this is the error. It's like 10 to the minus again 8, so it's not bad again. Okay, and this is how you can use the ODE45 to solve differential equations. And for this, this is for the system. You can solve the system of differential equation. For example, x prime and y prime, the derivatives are given here. You can write this one as if x of t and y of t, if you call it s, then your constant coefficient of s will be what? There is no x term, this is y 0, y term t squared, the x term minus t, there is no y term on the right hand side, 0. So you can write the coefficients 0, t squared minus t, 0, and s of t is x of t, y of t. So if you can think this is x of t, y of t, 0 times x of t, t squared times y of t. Exactly, it will give you the right hand side. Okay, we are just turning right hand side into a matrix times a vector. And by starting from 1, 1 and the time interval 0, 10, again you can call ODE45. The right hand side is 0, t squared minus t, 0, s. As you can see, we are defining this matrix times s, and you are just calling with the initial condition and the time span, and you can plot your solution like that. So it is not hard, it's so easy to solve any system, first order differential equation system or differential equation with MATLAB. Okay, and for the higher order equations, this is just for an example for you, for the motion of pendulum. In general, according to the Newton's law, this is the theta is the angular displacement, and if theta is the angular displacement, the derivative of theta is going to be the velocity, you know that. And here you go, this is how it will appear, the Newton's law of motion. And if you want to add the moving friction and sinusoidal forcing term, this is the forcing term, and this is the moving friction, you can get a second order differential equation. But in general, for all differential equations, we are writing firstly in the standard form. And what does its standard form means? The highest degree coefficient should be 1. That's why we are dividing the equation with m, and this is the standard form of the moving pendulum. Okay, that has the moving friction and sinusoidal forcing term. And for these ones, the initial conditions, the initial displacement and the velocity is given. And for that one we need to turn this one into a system. How do we do that? In general, what we are doing is we are calling, for example, so we need to turn all these theta terms into some other term. In this one, it's calling y1. So if you say that y1 is theta, y2 is going to be theta derivative, y3 will be theta second derivative. But look at the relation in here. If y1 is x and if the x derivative is y2, so x derivative will be also what? y1 derivative. So since I am trying to get rid of the x, instead of x derivative, I can write y1 derivative. And it will go over like that, okay? This is the idea. So y1 derivative, x derivative, y2, y2 derivative, x second derivative, y3. So you can go like that, and for the last one, you can write in terms of the y's. And for our equation, that one, y1 is theta, y2 is theta derivative, which means that y1 derivative is theta derivative, which is y2, right? That's why y1 derivative is y2. y2 derivative is theta second derivative. Theta second derivative is, you can solve it by moving these terms to the right hand side, and exactly we are doing that. Minus cy2, angular velocity sine y1, alpha sine gamma t. And you can write this one into the right hand side like that, and with that initial conditions theta 0 and v0, you can call the ODE. And with inline function, I define the right hand side y2, and I just gave some constants for the parameters, and you are calling f 0 to nt, and the initial conditions again I just gave something, and you can easily write the solution. Angular displacement is the red one, and angular velocity is the blue one. You can solve it like that, okay? You can copy paste from the MATLAB in here. And as a numerical method, in general, this ODE 45 and things are using Runge-Kutta, but all of it, it all started with the Euler method. This is the very basic of the numerical differential equation solver. And in here, what we are doing, we are just using the definition of the derivative again. You know that we have a differential equation in that form. And for the derivative, I am using yi plus 1 minus yi over h. And if I solve this one for yi plus 1, here you go. This is your Euler method. It's so easy, so basic, and you can easily write the code of the Euler method. It will take f function, t span, where do you want to solve, y0 initial, and how many iterations you will do, y equals y, h times f of ty. And in this one, you are updating the time, a times I times h. And in here, you are recording the time and the solution, okay? And you can call this program, for example, for our theta function. And if you do this, you will see a very similar result that what we get, okay? And the problem with the Euler method, so it's good if you have a linear function, but if there are curves, if your solution is turning points, has turning points, then the Euler method is not working very well. At that time, you need to modify your Euler method, or you need to get a higher order methods. And this is the modified Euler method. In this one, for each step, it's not going directly, so we are dividing the time steps so that it can capture the turning points if it has it. That's why this is the modified Euler method definition. K1, this is the same as the normal method, but for the K2, we are taking the average of them, K1 and K2. Ti plus h, yi plus k1, and this is how you can get this. So for k1, h times f of ty, for k2, f t plus h, y k1, and now you are taking the average. And you can test this program with these initials, and you can plot the solution. Okay, check that out. Again, this is just for an example to get an error, to get an idea. And of course, for the other than the Euler method, there are higher order methods. And in general, for solving initial value problems, we are talking about two types of errors. One of them is local truncation error. This is the error of each step. And another one is global truncation error. And this is the total error for the whole interval, for the whole solution. And for the Euler method, our local truncation error is OH square, and for the modified it is OH cube. And for the global is always 1 power less than the local one. So it will be OH and OH square. Okay. And for the, so that's why we are calling the Euler method first order, Euler second method, Euler modified Euler second order method. Okay, we are talking about according to the global truncation error. And this is a fourth order Ringo-Kutta method, which means that global truncation error for this method is OH4. Okay, and now you are dividing your time steps into smaller pieces, and you are getting into a different average for all different 4 points. And this is how you can code it. Again, the idea all in here is same. We are just defining all the necessary info, and this we are putting it into the loop. Okay, just get this idea, and this is how you can call the program and plot it. Okay, and I talked about Y order method in here. Please make sure that check them out. And again, this is just an extra session for you to get an idea how you can solve differential equations with a MATLAB.